Hello, everyone. Welcome to another episode of Q&A about future of science and technology. I have to say I've been kind of busy recently because we're getting ready to launch a product which I hope will be one little step towards some future for science and technology. Let's see. Sophia here asks, since you talked about the history of quantum mechanics, which I did just a couple of days ago, how about the future of quantum mechanics? Okay, let's try and talk about the future of quantum mechanics. So there are a couple of different things. One is understanding how quantum mechanics really works. That's kind of a foundational science question. The other is, how can we kind of use quantum mechanics in daily life? There are already all kinds of devices that make quite central use of quantum mechanics. Examples, OLED televisions and quantum dot television displays and so on make a certain kind of use of quantum mechanics. There are a variety of quantum effects that get used in different places. Another one is quantum tunneling. It's a phenomenon where you can have something where even though it's kind of like you're rolling a ball up a hill over a barrier and then down the other side, and the ball doesn't really have enough momentum to make it over that barrier. But in quantum mechanics, there's a small probability that the ball will kind of tunnel through the barrier to make it to the other side. And that's a thing that's been used for years in things called scanning tunneling microscopes. There are a variety of techniques for kind of visualizing things like individual atoms and molecules and so on that make use of this kind of phenomenon of quantum tunneling. That's a couple of places where quantum mechanics has been used. I think that there are various frontiers of the use of quantum mechanics. One is quantum metrology. Another, which I think is less hopeful, is quantum computing. But let's talk about quantum metrology. See, the fundamental thing, one of the fundamental things about quantum mechanics is things in quantum mechanics are very precisely, they're very precise in the sense that you can be in this energy level or that energy level, or you can have your spin up or down, but it can't be you can't be in between those energy levels. You can't have your sort of, at least in some way of setting it up, you can't sort of have your spin halfway between these things. It's kind of like it's on or off. It's definite. And that's very helpful when it comes to making very precise measurements of things, because you can end up with a situation where you say, okay, I'm going to have one quantized flux unit or two quantized flux units, but you can never have 1.5. And it's much easier to have something which can figure out, oh, it's going to be exactly 1, exactly 2, exactly 3, and so on, than something where you have to kind of decide, well, is it really 2.3, is it 2.4, whatever else. So one of the places where that's useful is in measuring magnetic fields very precisely. For example, magnetic fields very precisely, acceleration very precisely. Those are two places where one can imagine using sort of these quantum effects and this kind of all or nothing feature of quantum mechanics to make very precise measurements. What consequences does that have? Well, it gives one all kinds of possibilities for more precise positioning than GPS, for example, using kind of using features of either the Earth's gravitational field or just working out the acceleration that's been imposed on something, or in the case of magnetic field, using the Earth's magnetic field and so on, and knowing very precisely things about that. Those are a few. So I mean, I think the ability to have a very precise kind of quantum mechanics based measurement of things potentially allows things one can imagine, like a pocket MRI machine, for instance, is something one might imagine. One might imagine as I say, more precise positioning information, anything that involves sort of precise measurement of magnetic fields is sort of, I think, on the table. Let's see, what else? Well, there are a lot of things that become possible when you can make very precision measurements. Another class of things that one can imagine are things where you're kind of measuring features of molecules in things. So one of the big ones, which I don't specifically know of a kind of quantum metrology-based proposal for this, but I can imagine that one could make one, is being able to have non-invasive measurement of kind of levels of different kinds of chemicals in one's blood. So for example, right now, if you have your average fitness watch, it has those flashing green things on the back. Those are a PPG sensor. They are measuring the essentially change of color of blood as it is oxygenated and not. So measuring the your pulse as your blood is pumped in oxygenated form where it's darker in color, and unoxygenated form where it's lighter. And by looking at the way that that light is reflected back from blood underneath your skin, that sensor can determine when your pulse occurred and can measure things like your heart rate. You can also potentially measure the amount of oxygen, the oxygenation of your blood, pulse oximetry. Well, that's something that's just measuring, okay, how much oxygen is there in the blood? Is the how many red blood cells have got their hemoglobins full of attached to oxygen and so on. But the thing that's sort of a big challenge is, how about all the hundreds, thousands of other kinds of, possibly even more, other kinds of chemicals that are in one's blood, from glucose to all kinds of hormones, all kinds of nutrients, all kinds of well, ultimately fragments of proteins, bacteria, virus, all kinds of things. Everything ends up sort of going through the blood. Now, the question is there a way of making such precise measurements that you can detect, for example, the little vibrational features of different molecules and so on? One could imagine that with a new generation of kind of quantum metrology, that things like that might become possible. And that you can then have sort of a real-time display, not just of your heart rate, but also of hundreds of other attributes of, I just ate something. What did that really do to me? And so on. Well, another kind of area of quantum kind of applications is in things to do with computers. And there's sort of been a hope that the sort of feature of quantum mechanics, in which kind of there are many threads of history sort of operating in parallel inside the quantum process, that somehow one can take advantage of that to be able to run many threads of computation in parallel. That's been kind of the idea for 40 years or more of quantum computers. And it's not yet really panned out. There are a large number of efforts using about I don't know, 4 or 5 different technologies to try and sort of take advantage of that feature of quantum mechanics. The main challenge is, yes, you can have all those quantum threads run in parallel, but in the end, we humans want to know what the answer is, and we want to know a definite answer. And knitting together all those sort of threads of history is something that is not well accounted for in the standard kind of formalism of quantum mechanics, and is something which, as a matter of actually building quantum computers, is something that at least implicitly causes trouble. It hasn't been as explicitly realized as I think it should be, that there are these kind of potential limitations on sort of the quantumness of what you can do based on kind of what's involved in measuring quantum, the little quantum process. But that's kind of been a hope that there's sort of a way to do computations, which for an ordinary computer would have to be done each piece one after another, that you could do them sort of in parallel on a quantum computer. That hasn't really panned out yet, as I say. I mean, there are small experiments along those lines, but not more than that. There are also, and I happen to think that there are sort of fundamental theoretical limitations there, which are probably some of the most interesting science that can be discovered from this. Well, that whole direction has led to all sorts of investigation of kind of physics alternatives to the way that we build computers now with semiconductors and electronics and so on. And there are many interesting possibilities along those lines to do with using light, to do with using kind of individual atoms trapped in electric and magnetic fields and so on to represent the bits in computers. And there are lots of interesting directions there. Mention a few other quantum applications. Another one people have talked about for a while is various kinds of quantum cryptography and quantum being able to kind of transmit information while not really, but while having it be the case that you kind of can't intercept that information being transmitted, because if you did, the sort of quantum mechanics would reveal the fact that you'd tampered with it, and you'd be able to kind of and you'd be able to sort of know that had happened. There have been various experiments along these lines. I don't know how critically important. I don't think that that's. It's not convincing to me that that's the weak link in the security of lots of kinds of systems. I mean, I remember seeing, must have been 25 years ago now, kind of the idea of using sort of having, did the photon go down that piece of optical fiber or not? It's really a dark piece of fiber where there's just one photon or there isn't a photon. And trying to figure out whether, if there's just one photon, then as soon as anything kind of interrupts it, you kind of know that something went wrong. But I think when it comes to building practical, secure computer systems, I don't think that's the weakest link typically. I think with kind of the rise of sort of algorithmically based cryptography and the strong belief that that can't be broken for just purely algorithmic reasons, having nothing to do with the physics of anything, that's a sort of a good alternative to those things. Well, let's see. There are a variety of other applications people have certainly talked about for quantum mechanics. Again, quantum sensing is, I think, probably the most important, most obviously important direction, making use of kind of getting down to the level of individual sort of quantum bits in terms of sensing things, and just lots of stuff that you just wouldn't normally be able to tell. But if you can measure things sufficiently precisely, you can determine what's going on. And all sorts of things with individual molecules, all sorts of things with very small effects where you're trying to see whether did any light really get through this thing that absorbed most of it? Did any radiation get through this thing that absorbed most of it? Those kinds of things. That's on the practical side. On the theoretical side, I think the real question is whether there's what we can do in terms of making a better theoretical framework for thinking about quantum mechanics. What sort of happened historically is there was sort of the early days of quantum mechanics, nearly 100 years ago now, invention of things like Schrodinger's equation, Heisenberg's matrix mechanics, things like this, kind of classical quantum theory, in which one was using differential equations, matrices, techniques like that to try to sort of understand how quantum, very small phenomena, things, electrons and atoms, things like this work. What has happened in recent times is the rise of kind of quantum information and the idea that one can use much more sort of obviously computational concepts to think about quantum mechanics, and that one can really start with the idea of qubits and then sort of derive other features of quantum mechanics from starting to think about sort of the informational aspects of quantum mechanics. That's been a new thing of the last, 25 years or so. And I think it gives a different kind of way of approaching quantum mechanics that in some ways it's still just a formal way of approaching it. It's just kind of doing mathematics to figure out what happens. It's not sort of saying, why does it happen this way? But it's provided sort of a different approach. And that's led to the sort of entrainment of some fancy mathematics, particularly from areas like category theory, as a way to sort of characterize this sort of the the abstract representation of what's happening in a quantum system. Well, I tend to think that what we've been able to do with our physics project is sort of a big step forward in this direction, because instead of just saying, well, we build up quantum information as this kind of formal mathematical thing, we're really saying there is an underlying structure to do with these things we call multi-way graphs, branch shield graphs, and so on. There's an underlying structure that is the way the universe is actually built, and that gives you this kind of object that leads to quantum mechanics. There's vastly more to figure out about how that works, but I think that's the that's kind of it gives one a kind of a paradigm for thinking about these things that's extremely computational from the beginning. Now, there are all sorts of effects and things that suggests. One of them is we know in physical space that the speed of light governs the maximum rate at which information can travel. Well, we think that in branch shield space, this kind of space of possible quantum histories, possible quantum branches, that there's an analogous thing that we call the maximum entanglement speed, and that's something that, again, limits the rate of information propagation in branch shield space. And I suspect that that quantity is related to the limitations on quantum measurement processes, and therefore on how one can use things like quantum computers. So that's a thing which is sort of a direction to go in. What's happened in quantum mechanics in general is that the understanding of what happens when you have just one electron, two electrons, three electrons, a small number of atoms, it's become quite good in many situations, at least, when those things are not coupled together too strongly. It's been possible to get pretty good calculations in quantum chemistry and things like this, where one can really work out what happens to those small numbers of particles. By the time you're dealing with a large number of particles, and that's what's important when you're going to amplify some small quantum effect to a size that we can actually directly sense. When you're dealing with larger numbers of particles, it's been extremely difficult to come up with a formalism that can describe what's going on, except in very special cases. There are plenty of special cases to do with the propagation of electrons in solids, all sorts of other particular situations where, for example, in crystals, there's a kind of regular lattice of kind of a background lattice in which things like electrons move, and that regularity makes it sort of tractable to study the quantum mechanics of what's going on. But the general problem of quantum many-body problem has been very difficult to crack, and I think that's sort of a frontier problem that affects, well, lots of things. Again, there are special cases where progress has been made. An example of a very quantum many-body kind of thing is something like superfluid liquid helium, which is kind of the phenomenon of superfluidity is a sort of fundamentally quantum phenomenon. And certain aspects of that, superfluids have the feature that sort of everything moves together. And that means that one can somewhat reduce the kind of, you have to account for all of these many different particles to something a bit simpler in that case. And so that's been tractable. But the general problem of sort of dealing with large numbers of particles that operate according to quantum mechanics has been really hard. And I don't know for sure, but I have a suspicion that this kind of approach that we've taken will actually give one a good way to approach that. Now, of course, you have to rely on the fact that we can only do a certain amount of computation. And the universe, when it figures out what happens in some quantum system, is doing lots of computation. And the question is, can we sort of reduce that computation? Can we kind of figure out particular aspects of what the universe does where we can do a sort of cheap computation and jump ahead to see what happens? And exactly what kinds of cheap computations are possible is not yet clear. Let's see. Any other questions about quantum mechanics? All right, let's continue on here with some other questions about completely different topics. Brady asks, will AI tutors take over all education? Well, first one has to have one AI tutor that really works. We're working on that problem. It's AI tutors are frustrating because it's very easy to make a 5-minute demo. It's very unclear whether you can make something that will sort of keep a student engaged through a whole class. There are great things you can do with AI tutors. For example, you can immediately personalize kind of whatever you're talking about, something in algebra or something like that. You can immediately personalize that to the interests of a student. You can expect the AI to essentially get a model for what's going on in the mind of the student. So that, for example, it can figure out, oh, this is what you're confused about. The thing I should tell you to unconfuse you is this. It can also sort of listen to what you're saying about something and kind of get an idea of where you're at in terms of understanding it from the vague things that you say without you just doing sort of the multiple choice quiz as an assessment mechanism. So there are many things where you can do sort of continual, much richer assessment. You can provide sort of just the information that you need. You can kind of personalize things to make them more engaging for a particular kind of student. Can you really motivate a person to learn something when they're interacting with a computer? Depends on whether the person is internally motivated or not, I think. Obviously, games, for example, manage to kind of pull people along, or at least some kinds of people along. I mean, for example, I'm perhaps it's an admission of something. I never play games, computer games or others. It's just not something I find engaging. So that wouldn't be successful in pulling me along, so to speak. But there are many people who find that very engaging and for whom that kind of thing does pull them along, although the general gamification of education has not been terribly successful. So it has to be something, I think, richer and more engaging, more sort of human-like to a form of engagement to kind of pull students along with an AI tutor. But it's unclear whether people kind of, when all they have around them are machines, how motivated do they get? Some people are internally motivated and get very motivated. I really want to learn this. I'm really interested in it. Machine, just tell me what I want to know. Other people are like, why am I doing this? Nobody is encouraging me. No human is encouraging me to do this. And it would then be, it's a question of how much sort of human encouragement is really needed. How much is education really kind of almost a selling of knowledge type situation where it has to be a human doing it, and how much of it is just delivery, sort of convenient, ergonomic delivery of things. I don't think we know that yet. And there are many, many years of, probably 70 years now, of kind of failures in attempts to kind of machinify the education process. I remember when I was a kid, so this is probably, I don't know, I had these books about, the future from when I was, I don't know, 6, 7 years old in the mid-1960s. And I remember one in particular had these illustrations of the teaching machines of the future, and it didn't happen. And of course, different things happened. I mean, this is one of the things about sort of the arc of technology is you kind of imagine, oh, there's going to be this automated teaching machine, but actually what happens is instead that you get the web, for example, and you get Wolfram Alpha and things like that, and you get something which is sort of delivering something which is sort of kind of like what you might have imagined, except what you actually imagined was based on what already existed, and what actually gets delivered is something quite different. But so I don't know what I think AI tutors will be really important in a lot of kind of leveling of the playing field for education. There are right now, you can, if you're lucky, you can get a really great human tutor to help you understand stuff, but there just aren't enough human tutors to go around. And this is a way to kind of make that be a much more level playing field. And I think that's quite important. But I don't think it immediately solves the problem of how do you kind of motivate people to do things. I think, by the way, another thing that I think will happen, should happen, is that the very rigid, almost industrial form of sort of assessing Did you learn this? Do the multiple choice quiz, and how many questions do you get right, and so on. I think that mechanism, that very industrial kind of mechanism for assessing what you've learnt, I think that becomes something that is kind of a pre-AI story. And in the post-AI story, it's much more like the AI is kind of interviewing you. It's kind of doing an oral exam type thing, and it's kind of asking you questions, and you're chatting with it, and so on. And I think it's a much more flexible and in some ways friendly, much more personalized way of kind of assessing where you're at. Did you actually understand this or not? And so I think that's a thing where, as I mentioned, I think continual assessment becomes something quite realistic, where it's really you're kind of assessing where you've got to by the actual form of the interaction that you're doing in the teaching process, rather than, oh, you learnt this, now do a quiz, as that separate step. And I have to say, I mean, I've always thought that the sort of now take a quiz is for almost all jobs that get done in the world. That's not a good model of them. It's not a good way. It may be the best we've got in sort of industrial scale education to figure out where do people get to, but it's not a good model of what people will encounter sort of in the world at large. Let's see. Let's see, I noticed a question. Well, Cam is asking, will traditional classrooms still exist 20 years from now, or will everything be online? I mean, I've seen lots of online education, and my kids did a bunch of it, and there are lots of features of it. I think it can be with self-motivated people, it's probably can be quite successful. I think that still humans get a lot out of being around humans. And that's, I mean, I think, well, online education breaks into two major categories. One is sort of it's the asynchronous, you're with an AI tutor, you're on your own. And the other is synchronous, you're in a virtual classroom with a bunch of other students. And I think those are two rather different directions. And then there's are you sort of more directly around actual humans in real life type thing? And then there's the question of what's the role of teachers? Is the role of teachers to sort of recite knowledge, or is the role of teachers to kind of help individual students with over issues that they have, or is the role of teachers more in the role of kind of coaching and encouragement, and not so much directly content? And I think those things can get sort of factored out at this point. The role of teachers as a way to just sort of recite knowledge, even as textbooks became common, starting, I think big time sort of in the 1950s, that role started to decrease. I mean, before that time, if you wanted to hear kind of the lectures of Professor so-and-so, you had to go and hear the lectures of Professor so-and-so. You couldn't get the knowledge from them in some disembodied way. And then some bright publishing entrepreneur had the idea of taking lecture notes, I think it was from MIT, and publishing them as books. And then they could be sort of distributed more widely. And of course, when online videos, online courses, and so on came into existence, again, the delivery of knowledge in that way became much more distributed and much less necessary to have, all those separate teachers providing that delivery, except insofar as the delivery by a person standing in front of you, so to speak, is more compelling than delivery that you have to sort of read motivated by yourself in a book or something. I think that the sort of the flipped classroom idea of you kind of learn the facts online on your own, and then the classroom and the teacher is about kind of helping you work through actual problems that you're trying to solve or whatever else. That's been a popular thing. I gather it works quite well. I guess that at a time when AI tutors get to the point where they can do quite a lot of that helping you through things, that again becomes something that doesn't need to be in person, except insofar as it's kind of the human motivational aspect of it. And that kind of leaves encourage somebody to actually, yeah, you can learn this, it's worth learning. Maybe that comes, maybe it's really important for many people at least to see that come from a human rather than just the AI saying, hey, yes, you can do it. And the person is like, what do you mean? This AI is telling me that. What is it? No, it's not, it's not compelling. So that's a thought there. Meredith asks, are there enough guardrails in place for K-12 application of AI tutors? Good question. In the AI tutor that we have, it's pretty complicated. That's one of the issues. You have to have a primary AI that's interacting with a student. You have to have other AIs that are watching that AI, and you're also generating real-time. Another interesting thing is that you're generating kind of a real-time digested report of what the student did and what the AI did with the student, so to speak. And so if the you see it's kind of interesting to watch the behind the scenes of our AI tutor. You see the thing it's actually talking to the student about, and then you see its kind of internal discussion with other AIs, so to speak, about what's going on. Like the student is losing concentration, is losing focus, or the student just asked me something totally outrageous, or the thing I was about to tell the student is something I probably shouldn't tell this particular student, or whatever else. So yes, it is a complicated thing, and I mean, I don't know. We don't know for sure yet. We're just starting to test our AI tutoring system on actual students and so on. My impression is that that part is working fairly well at this point. It probably depends on the subject matter. I mean, the first major target for us is teaching Algebra 1, which is something where there isn't a lot of highly controversial content, and that is on topic, so to speak. So if it gets sort of highly controversial, it's probably very off topic, and that's a separate issue. How do you get the thing back on topic? If you're teaching other kinds of things, it might be more complicated because the actual material might be much more controversial, and it might be the barrier between what's sort of on topic and what's controversial might be much, much thinner. I'm not sure yet. Let's see. Weasel is commenting that kids need human encouragement to motivate them. Yeah, I think it varies a bunch. There's a spectrum, as there is with many things, of different people have different kinds of motivation. And sometimes that motivation can come from the very virtual kind of online, there is a person at a great distance, and sometimes it actually has to be the person is right there type thing, and so on. Let's see. The question here from Oskos. Do I think that medical ethics will change with the rapid advance of gene therapies? So the real question there is, I mean, let's be realistic. Gene therapy is still in its early stages. I mean, being able to edit genes kind of in situ, being able to go into actual tissues in a running, existing human, so to speak, and being able to modify the genetics of something so that you can avoid sickle cell anemia or deal with some retinal degeneration or something like this. There are things that seem to be quite successful in very specific cases where there is a very specific genetic modification that's caused the disease. Most diseases are much more complicated than that, and it's much less clear how to kind of just go in and zap the gene, so to speak, zap the single base pair change, for example, isn't what you're doing. Things like CRISPR, and there are many sort of follow-ons from CRISPR. CRISPR, what it's essentially doing, I mean, it's leveraging something that biological evolution already discovered was already existed in bacteriophages, viruses that infect bacteria. It existed actually in bacteria. It existed as a sort of very primitive immune system for bacteria, but we kind of harnessed that to turn it into this gene editing mechanism. It's a little embarrassing how many of the advances in in biology and biotechnology particularly were actually things that were invented by nature, so to speak, and we just found it and harnessed it for our technological purposes, rather than things where we just sort of started from scratch and said, how can we build this molecular structure that does this or that thing? But be that as it may, there's sort of a bunch of issues about how much can you edit, how well can you target the edits, all these kinds of things. Lots there that isn't really known yet, but advancing fairly rapidly. So there's the question of, modifying an existing human. And that's one question. Another question is modifying modifying genetics in a egg cell or something like this to modify a future human, so to speak, to make sort of designer genes for a future human. Let's deal with the human, the human who's sort of alive and running first. I've always thought that kind of the sign of something gene editing wise having happened was when we get kind of glow in the dark humans, and when it becomes sort of a fashion statement to have your skin glow in the dark. You can insert jellyfish genes into other organisms. There are fish that glow in the dark, which have had the jellyfish gene inserted into them. There is supposedly a plant that glows in the dark that you can get, and I ordered one. It hasn't come yet, so I'm a bit suspicious about what's happened to this plant. But there is supposedly, as of earlier this year, a plant that glows in the dark because it has jellyfish genes in it. And I've always thought it would be, I don't know whether it's terribly useful. Well, there are aspects of glowing in the dark that would be useful, certainly in things like optogenetics, where one's trying to insert genes that will show if a neuron is active, it'll produce a light signal, which you can then detect. And insofar as light can get through brain tissue and so on, you can potentially sort of light up. You can tell what the critter or ultimately person is thinking just by detecting those pulses of light from the modified neurons modified by editing their genes to sort of glow in the dark to produce light when they do things. I think that there are a bunch of diseases. I mean, one can start sort of ranking of the 100,000 or so classified human diseases, so to speak. It will be interesting to rank them, and I'm sure people have done this, by sort of how exposed they are, how much they are really accessible by making genetic changes. I mean, there are lots of pieces of genetics where, it's almost, oh, you should be lactose intolerant based on your genetics, but you're not, because you happen to use some secondary pathway and the genetics didn't play out exactly that way in you. Genetics is not as immediately determinative as one might have thought. And also the vast majority of kind of biological code is what programmers would call spaghetti code. It's a big mess with lots of different things contributing. And it isn't the case that you can just say, let me change that one piece of code and then I'll get this thing to happen. It's something I've been studying this actually a bunch recently, because I've been studying kind of a model for the foundations of biological evolution, which seems to also allow one to have sort of a model for the foundations of medicine, a kind of a formal model for what it means to make changes to an organism and see what happens, so to speak. And I think that may help inform the extent to which you can really say, let's zap the genome a bit and get what changes does that make. Most changes to genomes have all kinds of complicated effects. And knowing that, this particular one is going to have this one, I'll just make this one change, and then this one thing will happen. There are diseases where that's the case, but there are a lot where it isn't the case. Now, when you have kind of the sort of, I think there are fewer ethical challenges when it comes to sort of humans who are already the way they are, and you are trying to fix something that isn't going right, so to speak. More complicated is the challenge of should you make humans where you have kind of, not rolled the dice of nature, so to speak, but instead tried to engineer a human with certain characteristics. There's obviously a bad history to this. I mean, people people have been doing plant breeding for millennia. By the 1800s, people knew about animal breeding and were sort of routinely doing that, breed the better horse, the better cow, the better whatever. And so it was kind of a natural thought, particularly after Darwin and Origin of Species and so on in 1859, that one would think about kind of, instead of using natural selection to determine kind of how you got humans, use artificial selection, breed the humans, so to speak. Lots of bad things happened as a result. It turned out to be an ethically pretty awful idea. It's now the question is, if it's not kind of something that you're doing by sort of, if you're breeding the humans by constraining who gets to mate with who survives this, that, and the other, I think the world has sort of decided that that's kind of ethically off limits. When it comes to, if you have, for example, if you have a choice of 20, fertilized egg cells that you're going to implant, and you can make measurements on those cells, on those egg cells, and you can see, oh, this one has a high risk of developing some nasty disease. That one doesn't. What are the ethics of picking the one that doesn't? Well, I think one is a little bit saved by the fact that it's all very complicated. And when you have that thing that reduces the chance of cancer, that will also, make some other thing, make the person be able to run a marathon slower or something. There are lots of complicated trade-offs. It is a spaghetti code kind of mess of how genetic code works. So I think, at least for a while, there's a sort of the phenomenon of computational irreducibility that I talk about a lot. Just because you know the rules for a system doesn't mean you know how it will actually behave. That sort of saves one a little bit on some of the ethics, because you make a change. You say, I really want my kid to have green eyes. Okay, great. That's a thing where one pretty much knows what the genetics of that have to be. Then you can pick that one. But just picking that, if you've got a lineup of a bunch of egg cells or whatever, then you're going to get a bundle of 6 billion other base pairs in there, and having picked that particular aspect is not really determinative of everything else. Now, if you say, let's get a little bit more extreme, and let's say we can make more careful edits and so on, and we have this giant dashboard, and it's kind of, you go into the child factory, so to speak, and you say, I want, I'm going to click all these things like even more detailed than buying a car or something like that. There are all these options. Do you want the kid to have red hair? Do you want the kid to have this? Do you want the kid to be able to do this, that, and the other? First thing to say, again, I think it's going to be a little bit more complicated than one imagines, because I think many things come with trade-offs. You want the kid to be, oh, I don't know, you want the kid to be really smart in this particular kind of way, if that's something that can be determined by a small amount of genetics. Or you want, well, that will mean that they're kind of a geek, and so this will be bad for the kid. I think it becomes difficult. It's not it's not something where it's kind of there's an obvious right answer, so to speak. There probably are some things where certain nasty diseases, you can exclude those nasty diseases. That's something one's already doing with lots of fetal genetics kind of testing. That's already kind of a thing. I mean, the earlier one can do that, probably the ethically happier one is about it. It's a complicated thing, because in a sense, ethics is like, often we don't want to do something that, if done to us, would make us feel bad. So, if we know what would make us feel pain or something, then we feel like we don't want to impose that on other things that are like us enough that we can kind of infer that they would feel pain as we feel pain, so to speak. And that's obviously an issue with knowing, how that works for animals, fetuses, all these kinds of things. It's very unclear. It becomes very definitionally complicated. I think that one of the things that's often an issue, and it's certainly I certainly notice when people are thinking about animals and animal rights and so on, at the point where we can sort of decode animal language and we can have a serious conversation with our cat, we might have a different view of kind of the how like us the cat really is, and how much the ethics that we would extend to other humans should also extend to the cat. Could go either way, I think. But in any case, I would say that this whole question of kind of, should you design a human to be a particular way? I think the bad news is it's really hard to do it, but that's also good news, because it means you're really stuck kind of rolling the dice of computational irreducibility and not being able to say, I will design my Frankenstein monster type thing with very precise kind of, in a very precise kind of robotic way. So I think that's a few thoughts about that, at least. Let's see. Mad Monk says that people have created glowing dot rabbits. Okay. Yes. Indeed, there are. You can absolutely get okay, the rabbits glow green under ultraviolet light, apparently. There's a question from Kathy. Could bacteria or viruses evolve to outsmart all our medical advances? Biology has been pretty clever about this. The immune system, the human and mammalian adaptive immune system, is pretty universal. It's these molecules that have a certain shape, and there are 10 billion or a trillion, depending on which subsystem you're looking at, of differently shaped molecules. And it turns out that that inventory of possible shapes of molecules, of antibodies or T cells, whatever, is kind of enough that it can kind of recognize, here's a protein with a certain shape, and it's a protein that isn't like a protein that's in me, but is some kind of alien, foreign, bad protein, so to speak, that I should attack with the immune system. There is a certain universality to that. We don't really completely understand how it works. I'm actually curious to try to figure it out. This kind of space of possible shapes that proteins can take on, and the space of possible shapes that the immune system can discriminate. But it seems that sort of any shape that is thrown at us by biology, as a protein, so to speak, and biological things are biology on as life as we know it is always made from proteins. That it seems like our immune system is sort of universally able to do that recognition of protein shapes. So that's a piece of good news. Now, there are certainly things where one can sort of hack biology and try and find these kind of weak links. It becomes a problem very much like computer security. It's very much like, insofar as we managed to decode a lot of biology, and we're still not quite there yet, it becomes like computer security, where it's like, here's an operating system. Even if you see the source code for the operating system, how do you find a hack that allows you to worm your way into the operating system and take over, for example? Well, the only way that, that problem is sort of similar to the problem of designing drugs and designing drugs to treat diseases and so on, because typically a drug to treat a disease, that the most common thing it will do is be of the right shape to bind to some particular site in some particular molecule and make it more active, less active, whatever else. And so we haven't been terribly successful at sort of hacking biology to the point of being able to make designer drugs that that will target some particular kind of feature of some particular kind of receptor on some cell or whatever else. There's obviously some success. There are a couple of thousand drugs that have been, approved for use in humans, but it's a lot of work to find another one. And there's a lot of problems and a lot of candidates that don't succeed. So the idea that one can just sort of come up with a drug, a molecule that will be kind of oh yes, it will do exactly this thing, that's proved really pretty difficult. People hope with a series of different approaches, rational drug design, combinatorial chemistry, now AI-based drug design, sort of designer proteins based on giving a text prompt that instead of generating sort of a big essay will generate a protein structure, these kinds of things. These are all efforts that people have tried to sort of solve the problem of make a protein that does what you want it to do. So far, there hasn't been a kind of a slam dunk solution to that. So when it comes to, can you, for example, is there a way of, for example, is there a way of creating, the virus, the bacteria that's going to sort of hack biology? That's one thing. Then there's the question of, will nature throw that up of its own accord? In terms of creating it, well, that's the story of bioweapons and so on, and there's this sort of, like drug design, it's something where you could do it ab initio, or you could try and find a thing that is some nasty toxin that some particular kind of snail uses, and then you can bottle that up, so to speak, as and weaponize that. I think that the thing, well, let's see, in biological evolution is a way of sort of finding solutions to things, finding that way of managing to have the bacterium defend itself against the bacteriophage viruses that are attacking it, these kinds of things. Biological evolution goes through all these different iterations to try to find something that works. I've recently happened to have studied kind of the foundations of how that works and why that works. I think I now sort of understand that. It's quite an interesting story. But as a practical matter, biological evolution is able to do certain kinds of things, not able to do other kinds of things. You get a certain number of iterations that you can try. Like in the history of life on Earth, about 10 to the 40th organisms have lived. So there have been sort of 10 to the 40th different tries at different kinds of things, which succeed or fail. And that gives you some kind of sense of scale. I think about a trillion generations of organisms have lived. So that's sort of a sense of scale of what you get to try there. Now, one of the things that certainly is a story of in the sort of this, there's what happens naturally in biological evolution. There's what we can do by explicitly designing things. And there's also what we can do by artificial selection. So for example, if we're breeding viruses, for example, we can do, the equivalent of 1,000 years of what will be natural selection, we can potentially do in a matter of months by just sort of applying, by saying, infect something with these viruses, sort out the cells where the virus did this or that, modify the modified version of the virus, this modification did better, this natural modification did better, pick out that one, run that one again, and sort of enhance, do breeding effectively of viruses. So, now of those three different directions, I think the question of will natural nature throw up a thing that will kind of defeat our immune system? I think there have been many threats to our immune system, and there's some awkward ones like AIDS, for example, which specifically attacks the immune system. But I guess I think that the sort of coexistence of viruses with higher organisms for the last billion years does tend to suggest that sort of left to their own devices, it's unlikely, at least, that sort of the virus that can defeat the immune system will arise. Now, an interesting question is, could there theoretically be a virus that defeats the immune system? Can there theoretically be a way to sort of avoid this supposedly universal kind of shape matching mechanism of the immune system? I don't think we know. I think that requires some better knowledge of the excuse me. To know that requires better knowledge of how the details of how the immune system actually works. Let's see. Just asks, will AI-driven biological evolution make Darwinian evolution obsolete? How do we prevent the automatic synthesis of biological viruses by AI? Yes. Well, it is a problem. I mean, if you have the practical situation of being, a company that synthesizes DNA, for example, how do you check that you're not synthesizing some really nasty new killer virus? Really hard to do. You can check that it doesn't match smallpox. You can check, it's rejected if it matches smallpox. But this is again a story of computational irreducibility. If you're presented with the genome and somebody says, just make this genome, and you say, well, is that a bad genome or a good genome? You really can't tell, other than particular sort of blacklisted cases where it's a known bad genome. You really can't tell. Now, is it, as I was saying, I mean, I think that the story, so it's a question of whether kind of simulated evolution will successfully outrun actual evolution done with proteins and labs and things like this. Not yet. We're pretty far away from being able to simulate the reality of biology. We can, at best, simulate. I think I've gotten somewhat a good leg up on simulating the essence of what's going on in biology, but it's not the actuality of what's going on in biology. It's not something where it produces a thing that actually would eat things and so on, and it's very much more idealized than that. Just a second. Let's see. Elsie, when, if at all, do you anticipate we'll have mostly softwarized humans, meaning that we can reprogram ourselves just as easily as we can reprogram computer systems? It's not so easy to reprogram computer systems. If you have a running computer and you say, I want to change this computer and what it's doing, it's not so easy. I mean, if you wanted to go in and patch a running operating system, good luck. It's unlikely to work. It's more likely to crash, which in the human case would probably mean die. So I think that there is a very complicated issue. If you start to be able to modify what's happening in the brain as an external thing, and you say, well, I decided I eat too much chocolate. I want to just press a button to have my chocolate eating, craving, so to speak, reduced. It becomes a very complicated thing to know kind of what's free will, how does this all work? If you get to just select with a slider how you feel about something, I mean, it's what does that mean? You felt it this way about how you should feel about it at that time, but then the actual feelings you had are changed. And how does that loop really work? I think this is a bridge we haven't crossed, and I think it's a complicated ethical story. And I think then we have to ask, what is ethics? Is ethics what we think we have a view of ethics based on the way we are as humans today? If we were different than we are, we probably would have a very different view of ethics. If it was the case that, for example, I don't know, we knew, let's say, for instance, we knew precisely how long we would live. and nothing could change it. That would, I think, present a different kind of a set of issues in ethics that are different from the ones we have. If certain things we knew in advance, they would have a different consequence for ethics. And I think there's sort of a question of ethics from what we are today. We project a certain way of how we think things should be now and in the future. But if we were different than we are, then we don't have that same sort of anchor for knowing what ethics should be like. And ethics for the different human will not be the same as ethics for the human as the human is today. Let's see. I have to unfortunately go soon, but let me maybe try and take one more question here from Mike. Talking about biological evolution, can this help humans break the longevity limit for humans and say, get humans who can live a couple of centuries? I don't know what it's going to take to do that. I'm sure it's possible. It is surprising the extent to which we have kind of a biological clock that changes the way we are as we age. We know we have short-term biological clocks. We know we have a circadian rhythm that operates on a roughly 24-hour basis. We know we have monthly rhythms. We know those kinds of things. And we know that, as we're kids and mature and so on, we have things that are like, take a decade or something. We know that, even something like, I don't know, the plates of the skull, I think, finally kind of join up at around age 40 or something. There are all these clocks and timers that exist in us as humans. And it is a little bit kind of shocking to realize that those timers just keep operating. When you have a face recognizing program, the facial features system, it's pretty accurate at saying how old a person is. It's picking up a lot of details of how bone structure tends to change and so on. These are things that sort of inexorably seem to happen. And biology, it's unclear exactly why we age. There are different phenomena going on. There's genetic damage, there's oxidative damage, and then there are specific forms of genetic damage which aren't probably as straightforward as was first imagined, of just these end caps for chromosomes kind of falling off and progressively falling off as more replications happen. It isn't quite as simple as that, it seems. But kind of there are these various clocks operating that seem to and the question then is, well, can we just stop those clocks operating? Most likely, knowing how biology works, it's always a very complicated trade-off. You have those clocks operating and they operate this way because if you stop those clocks, you would get lots of tumors, let's say. Or if you stop those clocks, some other thing would happen. Or even, now it could be that some of the things that those clocks are there for, so to speak, have been successfully selected for, are things we don't care about or don't want anymore. For example, it could be that in the past, you wanted to get rid of the old organisms because otherwise nothing new happens in the world. Everybody just says, I learned this when I was a baby bird, and I'm never going to try anything different, when I'm a 40-year-old bird or something like this. And that if sort of it could be that sort of in the course of biological evolution, that having organisms stick around forever is a way to kind of prevent certain kinds of flexibility and innovation. Maybe that's true with humans as well. But it's I think most of us humans, well, if we're having a good time, we kind of say, let's continue this as long as possible. And one would like to see effective human immortality. Of course, it will have all sorts of societal consequences that I think people, it's an interesting question, sort of how it affects one's view of one's life if one thinks it's infinitely long. And like, I'm not going to bother to do this now. I'll do this a century from now. Or, in my long life, I will have done almost everything. You know, I will have had every profession. I will have had, et cetera, et cetera, et cetera. You know, it's a different view of things when you start thinking on those timescales. But you know, it's unclear whether aging is a biological bug, a consequence of the sort of physics of biology, or something that is a trade-off that maybe is a trade-off that is irrelevant given sort of modern civilization and the, you know, it's like there are plenty of things that are trade-offs because for most of human history, there wasn't things like clean drinking water. There were parasites everywhere. And so there were things that biology had to do to kind of deal with that, which are sort of irrelevant in most of well, much of the world at least. And so insofar as those things are what is now our environment, what is now the, you know, one can make changes. I unfortunately have to disappear here, but a lot of interesting questions, which I will try to address another time. Thanks for joining me, and bye for now.